the water for food. And in this section, we have two presentations by Sonia Lori and Jeffrey Tahtouh. And we'll start with Sonia. Sonia, you have the floor.
So all the speakers, hello Sonia, hello Jeff. Please stick to the time, 5 minutes. We're running a bit late.
Okay, can you hear me? This is Sonia.
Yes.
All right, I'll do my best to keep to the time. I just started a timer. Thank you to everyone for allowing me to present today. I'm excited to talk about my research. The title of my presentation is The Effect of Municipal Treated Wastewater on the Water Holding Properties of a Clay Calcareous Soil. My co-authors are Dr. Amjad Assi, Dr. Rabia Mohtar, Dr. Christine Morgan, and Dr. Anis Jantrania. And as a preface, I came into this being interested in looking at the nexus between food and water, particularly wastewater, and in my preliminary and literature review, looking at wastewater irrigation on different kinds of soils and different crops from a variety of perspectives. The jury seems to be out on an overarching consensus on whether it's good or bad. And this is something I'll talk about in my conclusion, but it really comes down to every place is different, and you have to look at what your situation needs and what is best for it. And so the objective of our study were to quantify the impacts of using treated wastewater and the available brackish groundwater at our study site for irrigation on a soil. And the location was San Angelo, Texas, which is in West Texas, and the location was a cotton farm, which is a pretty important cash crop in that region of Texas. And our second objective was to dig a little bit further and evaluate and compare the field scale impacts of irrigating with these two types of water, compare them to the rain-fed irrigation on this farm, and the impacts of using these three different waters on the overall water use and plan in the region. And so what you need to know about the soil is that it has lots of clay, upwards of 50% in the lower horizons. We looked at the top three horizons, so the plowed horizon, the A horizon, and the B horizon. So we went down to about 72 centimeters of depth. It's limestone derived. He tills the land with a disc harrow, and he uses drip irrigation with his groundwater and his wastewater. The wastewater comes from the San Angelo wastewater treatment plant, which uses a traditional aerobic secondary treatment. They discharge that water into water canals, which go to the farms, and the farmers pump it out. And this particular farmer uses an on-farm disc filtration to protect his drip irrigation from any particles that might come into it. All right, next slide. Oh, I'm back. Our methodology, we used a relatively new methodology in this discipline that's called the pedostructure concept that was developed by a few people, including Dr. Mohtar. The device we used is called the type of soil, and what we extracted from the type of soil were two curves. One is the soil shrinkage curve, and one is sorry, it's slipping my mind. The water soil shrinkage, which you'll see right here, it goes upwards to the right, and the help me out, Dr. Mohtar. It's slipping my mind.
Shrinkage and swelling.
The swelling curve. Thank you. And so what we were able to extract from these parameters using the type of soil and using some thermodynamic analysis was the permanent wilting point, which is a location in the soil where the plants can no longer access the water. The field capacity, which is the amount of water that the soil holds after gravitational water falls out. And with these two parameters, we get the available water capacity, which is basically an amount of water that is held in the soil that is available for plants to use. So what did we learn? Next slide. You'll see here we've got three columns for each of the types of water and two graphs for the A and the B horizon. We found that the rain-fed soils, the ones that weren't irrigated, had the highest available water capacity. And we disregarded the top section of the soil just because it had a lot of disturbance, and these two horizons held their structure a lot better without the tillage, so these are more representative of what the soil properties are. You'll see that the treated wastewater and the groundwater both have a reduced capacity to hold water. It doesn't look like too much, but when you extrapolate it to a field scale, it does add up to a lot. And so this is what we found, is treated wastewater and groundwater reduce the capacity of the soil to hold water, and the groundwater seem to have a little bit more of an impact than the treated wastewater. So in conclusion, keeping in mind that the farmer is interested in making a profit, so the rain-fed is the best in terms of soil health and its ability to hold water, but he only produces about 1 bale per acre using rain-fed. Whereas with treated wastewater, he produces 3.5 bales per acre, and with the groundwater, he produces 3 bales per acre. So in this situation, with the parameters at hand, the farmer can use this treated wastewater and know that it's a little bit better for his soil than the groundwater, and it's a good and relatively inexpensive reuse for the water for both the city and the farmer. And so in this particular situation with this soil and this water available, it's a suitable alternative for irrigation water. Thank you.
Thank you, Sonia. Jeffrey?
Hello, this is Jeffrey. Can everybody hear me?
Yes.
So, my name is Jeffrey Tahtouh. I worked on the research. I researched the impact of brackish groundwater and treated wastewater on soil chemical and mineralogical properties. It was the same location as where Sonia's research has been done, but at this point we're focusing on the chemical and mineralogical perspectives of the soil. The objective was to assess the impact of using non-traditional water for irrigation on the chemical and mineralogical properties of a calcareous clay soil from West Texas. Here in the slide we can see our parameters. We have our soil that we used, which was the Angelo series. We used that soil because it's the most dominant in the county, covering about 16% of the Tom Green County. Also, we can see our sources for the water used for irrigation. The groundwater, which was moderately brackish, as we'll see in the result, is coming from the Lipon aquifer, and the treated wastewater is coming from the water reclamation facility in San Angelo, where it's treated, where it's secondary treatment, and it is delivered to the farmers by these man-made canals, as illustrated in the picture on the right-hand side. But this is all has been done to answer the question of what is the quality of soil that is left behind after the use of alternative water, and to look at the bigger at a bigger scope to answer the question, is this a good solution to help bridge the Texas water gap? For methods and methodology, so we collected samples, of course, from treated wastewater, as we can see in the image, straight from the man-made canal. And for the brackish groundwater, it was collected from a nearby groundwater well. We ran several tests to have these chemical results or chemical analyses of the water using titration, conductivity, and ICP. From a soil perspective, we collected 3 samples per experimental group, which are the 3 top horizons, A, P, A, and B. And the 3 experimental groups were rain-fed, which was our control, and then brackish groundwater irrigated, and then from another field, which was treated wastewater irrigated. And we ran several tests. the hydrometer, for example, to come out with the results of the texture. And we ran several other tests to find out the chemical perspectives of the soil. Also, we ran the XRD, which is the X-ray diffraction, and K quantification, which is potassium quantification, to identify the clay mineralogy of the soil. As we can see in the image, the soil clay mineralogy here, they are labeled, there are different labels because we treat the soil, we do different treatments on the soil to identify which are, what are the clays, specific clays in the soil. So what we came out with was first focusing on the water results. As we can see, the brackish groundwater, the brackish groundwater results are do go over the irrigation water quality criteria set by the Food and Agricultural Organization. They have a higher salinity, and as we can see, the electroconductivity is higher. But let's keep in mind that the calcium and magnesium do counteract the effect of the sodium, which, as we shift to the soil results, as we can see in the SAR, or the sodium absorption ratio, we see that the treated wastewater has a higher SAR compared to the brackish groundwater, and that's a result because of the calcium being lower than the sodium in the water for treated wastewater. And all the results from a chemical perspective show that the soil is in good health, because we can see that the electroconductivity in all the soils don't supersede or exceed the 4 decisiemens per meter, and the SAR are lower than 13, and the exchangeable sodium potential or sodium percentage is lower than 15, which indicates that the soil is in good health while using treated wastewater or brackish groundwater for irrigation. Shifting to the mineralogical perspective, as we can see that all the graphs look the same. We have the same peaks. We have the smectite, the elite, and kaolinite showing in all our samples. And again, there hasn't been much shifting in the chemical and mineralogical perspective. So to conclude, the key takeaways are that unconventional water sources such as treated wastewater and the brackish groundwater can be used as substitutes for freshwater irrigation in semi-arid and arid regions when the conditions are right. So here we had a clay soil which was high in smectite, and which indicates as fairly stable, and it plays a major role in the fertility of the soil. So using brackish groundwater or treated wastewater didn't do any major changes or didn't decrease the productivity of the soil. And finally, we can say that the treated wastewater is much more suitable than the brackish groundwater because it has much better quality when we compare the results to the criteria that has been set by the Food and Agricultural Organization. Thank you.
Thank you, Jeffrey. Thank you, Sonia. So Q&A 4, we'll start with AUB. Dr. Bastur.
Okay, thank you for the presentations. Regarding the sewage water and brackish water, I'm very glad that you connected the results to the SAR of the water, because we have always to find the ratio between sodium, calcium, and magnesium in the water. My question is, how many years, how many seasons did you run this experiment? For how long?
Sonia, Jeffrey, Dr. Bashir is asking for how many years? 10 years.
10 years?
Yeah, so they've been irrigating with this water for over 15 years. We just took samples from 1 year, comparing the rain-fed sections have never been irrigated, so we used that as our control, comparing 0 years to 15 years.
May I ask another question? Okay, well, there are many places in the world where they use sewage water raw, as is, very common. What do you expect this to happen? Is that a good practice regarding the physical and chemical properties of the soil? Forget about now the health aspect.
Sure. I'll answer, but I think Jeff should also chime in. That was one thing I looked at, kind of a range of treatment options, because that's another variable that that affects the question of whether this is good. And I think it depends. What I see from a biological standpoint is that it seems to be a good thing. From a physical standpoint and water holding capacity, from what I saw, which was limited in the research, it doesn't seem to be good, but I would say the jury is still out. I don't know if we have any conclusive evidence on the effect of raw wastewater on the water holding capacity of soil.
Chemical perspective and the physical perspective. First, we have, as we mentioned, and Sonia mentioned in her presentation, that it depends on first what kind of situations you have at hand. Also, this is talking about the climate that you have, the type of soil, the organic matter, the mineralogy, and also from the other side is how well is your treated wastewater. And you can see in some of the other parts of the world, the treated wastewater is not treated to the level that is treated here in the US, for example. So we can say that the water that has been used in this research is of high quality treated wastewater.
Thank you.